Hello, today we're going to have a contest. It's been a while since the last one. And I hope I do well this time. Because the previous one was not the perfect outcome. And we got this huge drop down. Well, here we have here a lot of cool competitors, but I did not call anyone for a duel. I only called Leo Pro, Fast Math and Termax, but they refused due to another activity, mathematical one. The champions, world champions. So I wanted to compete with them. However, they're busy today, so no duels today. I hope everything works. I hope everything works. The computer's too slow. Well, it's fine. Let's go. English. Here we have an invisible row which continues this link. Good, okay. 10 seconds before the start. I'm not feel prepared, but it's too late to undo and to cancel. Chocolate and vanilla love cakes, 2 to the k plus 1 cakes. Each of them initially had take 2 to k cakes. They want to redistribute. Yes. Chocolate gives half of your cakes. Okay. So I need to read number k and number x. And I need to print pair of vector of vector of bulls. So let's go. What do I need to do? I need to store number y equals this, and while x is not equal to y, I need to take the minimum of them. Else x minus y plus equals y, and also we ans, and here I say ans. So this means that chocolate gives half of your cake to vanilla. Chocolate gave half of her cake to vanilla. Good. Then I need to reverse it. Good. And I need to read it and print it. Okay, let's go. So I need to print on that size and for bool b for months. What do I need to print? b+1. Okay. 2210, 3221. Oh no. Two two one zero 3221 212. Yes. Is it long? Did I only use longs? Yes, I only used longs. Good. Problem B. Q? Q is not good. Okay. Antiomony wants to learn swap. For an array B of length m, we perform two operations. Swap bi and bi+1 and swap bi and bi+2. We need the minimum number of operations required to sort array B in non-decreasing order. G of B is the minimum number of operations to required to sort B only with operation first. The array is perfect if B f equals G. So we have a subarray and we need to determine whether it's perfect. Okay, the easiest way to create a perfect array is to take the ID permutation and make several non-intersecting swaps. Is it true that it is enough? For example, if I have 3, then anything. Is it obvious that I need to swap? Well, for example, in this case, I obviously need to only swap 3 and 1 and then 3 and 2. But I don't need to swap these two, because I still need to make this swap. So it's some sort of... Okay, if element is... So in which case I really don't need operation. So I really need an operation of... If I have a decreasing sequence of length 3, then I need this operation, I think. Subsequence. But if I don't, then I don't need it. Yeah, because it looks like an increasing sequence and then another increasing sequence. Right? No. So what about 3, 4, 5, 1, 2? Actually, I need... There is no decreasing subsequence of length 3, but I still want to do... For example, in this case, I want to move it here and then move it here. So this is not the only case when I want the big swaps. Maybe it can be reformulated in terms of cycles. Somehow it's very hard. Okay, let's skip and let's look at C1, and then we'll return to B later. Maple is given a rooted tree of n vertices from 1 to n, where the root has index 1. Each vertex of the tree is labeled either 0 or 1. Unfortunately, Maple forgot how the vertices are labeled and only remembers that there are exactly k0s and n minus k1s. Good. For each vertex, we define the name of the vertex as a binary string formed by concatenating the labels of the vertex from the root to the vertex. Yes. Yes. The beauty of the tree is equal to the longest common subsequence of the names of all the leaves. Longest common subsequence? The task is to determine the maximum beauty among all labelings of the tree with exactly k0s and n minus k1s. Well, it's interesting. So I have a tree. So first of all, the root is basically, I choose anything to put in the root. And it's always adding 1 to all the common subsequences. Then the question is, what do I do with the children of this vertex? It makes sense to make them all equal, right? Because if I make them different, well, it just doesn't make sense. So if the biggest common subsequence starts with 0, why don't I just move this 0 to the to this place? Right? So it's like a backpack, I think. So let's look at the top leaf. Assume that it is height 0 and this is height h minus 1. Then I have h numbers, the size of each layer. Then on each layer, I have some numbers, so it's a0, a1, etc., ah minus 1. And then I want to construct exactly k from these numbers. And what do I want? I want to find the number of ways. The maximum beauty. The maximum beauty. So I want to find, so I have k and n minus k, and I want to find the maximum number of elements that I can put here or here. Yeah, basically, obviously, I can do h minus 1, and the question whether I can have h is some backpack problem. Let's see how it's formulated in C2. So the sum of all elements is at most 200,000. 200,000. Okay, let's just do it the fast way for now, because I forgot how to do it. So T and K. Then I need the vector P. Let's say that it should be a have size n. Then I need to find ans. It's just an int, right? So I need to give P and K. And then I print. Okay, here, what do I do? Okay, so how do I do it? So first of all, I need to construct the array. How do I construct an array? I need to find the number of vertices on each layer and also the top leaf. So let's find the degrees of all vertices. So degrees and layers of size n. Let's go now through the vertices. Also height n. Can I find the height? Of course I can find heights because it's given as the parent. Yeah. So let's go through the vertices. So I say that hi is hpi plus 1. Then I say that plus plus lhi, and I want to find the degree, and also plus plus dpi, and then I want to say again so if di equals 0, then h equals minimum of h. So I want to find, so h minus 1. So h is the depth plus 1. Good. Okay, now I know it, and I want to make the backpack problem. So what do? I want to say that, let's say that while layer dot size, I just want to say that L dot resize h, and I want to ask if achievable L, K, and n minus k, then return, I just want to return answer, which is h minus 1, and if something is achievable, then plus plus ans, and then return ans. And we need to only construct the function achievable, which consists of VIL and 2 ints. So what do I want to return? I want to return whether it's possible to divide it into 2 subsets of sum at most x and sum at most y. And in order to do that, Let's just first find the total sum. Accumulate. I don't know accumulate, okay. So, first of all, let's just make vector achievability of size x plus 1. Let's go through all of these elements and say for int j equals x, j is at most 0 minus j, if j plus I is at most x, and aj and this is at most x, then aj plus I equals true, right? So basically I can start with, so j plus I should be at most x, so j should be at most x minus I, something like this. Yeah. It can be done with bit set, I think. Is it okay to do it with bit set? Or it sounds strange? So with bit set, it's something like 200,000, right? With bit set, it will be slow because of the multitest, I think. Or no? No, it's not really. So I have a bit set of size 100,000. And I want to 100,000 times also make some operations. It's too slow, right? Yeah, it's a bit too slow. Okay, now we go through this array and say if AI and if S minus I is at most Y, then return true, else return false. So 3, 2, 5, 1, 2. What? What is the smallest tree? 5, 4, 1, 1, 1, 1. And the answer should be... Okay, let's only leave this one. What's happening here? So we have h equals 2, and the answer is 1, and we want to check whether it's achievable. Why is it not achievable? Because I need to say that a0 is true. Right. 2, and now 3, 2, 5, 1, 2. Okay, let's submit C1, and then we think what to do with C2. It should be fast enough, right? Oh no, do I have a cubic complexity? Do I have a cubic complexity? I hope no. No, it's of course quadratic. No, it's 100,000 times 100,000 and divided by 64, right? So it's like, and is it 100,000? Also this array is increasing. Yeah, this vector is increasing as well. We know that it is increasing. I think we can speed things up then, right? So basically what we want is we have a0, etc., ah minus 1, and we have two numbers a and b, and we want to put as much as possible in the eighth part. We want to find the maximum number which is at most a, which fits in a, right? This is what we want. A maximum number which is at most a, which fits in a. How can we do that? So there are big guys. So let's say that we're interested in how it's done. So it's 1, then some number bigger than, at least 1, then even bigger and bigger and bigger. I really don't remember what we do there. So basically, we can say that it is at most 100,000, right? Let's say that we want to... So let's say that we have numbers which are at least square root of a and which are at most square root of a. So these numbers can be processed easily. These numbers cannot be processed easily, but there are not many of them. Ah, okay, this makes sense, I think. So let's rewrite it. So int max at most vi l. Okay, let's see const l and int x. So first of all, if x is greater than y, then swap x and y. It doesn't matter, I think. It doesn't matter at all. So let's say the index equals 1 plus I. Actually, this can be done here. This can be done here. This can be done here. So I want to find int x equals max at most l x, and that is the number I here. And I want just to return, is it true that s minus x is at most y? That is what I want to return. For that I need to find the sum. So here I want to find the maximum number which is at most this and which is achievable. So let's do it. Let's find integer square root of s. So first of all, so should I do it with bit set or not? I think I should do it with bit set and don't care much. Let's do it with bit set. That's it. So for that, I want to, if x is greater than y, then swap x and y. So x is at most 100,000 just because it is 200,000, right? Ah, no, it doesn't work this way. It doesn't work this way. No, no, no. Or it works. No, it's not. It's not. So let's think again. So I have some vector. Let's have some vector, long vector. And I have some number s and k. And I want for each element copy it k times with step s. How do I do that? Okay, there is a way which is very unlovely. Okay, let's go. So for int v, so there are numbers which are strictly less than s and which are at least s. Let's start with strictly less than s. So see, if I is less than s, then plus plus cnt of I. Then okay, then let's go. So what do I do? So first of all, for int I from 0 to s, let's start with 1, I think. So so if cnt I, what do? I can create a vector of repetitions of size I. So what do I want? I want to ask if I have this element, how many elements with the same residue were there in the previous k steps. In previous k steps. In previous CNT steps. So k is CNT. CNTI. So we have k times. We want to step back by k. Ah, no, we want k times step back by I. Yes, so we go through all elements. So what do we look at? We want to look at repeat j percent I. So we look at it. we look at how many repetitions were there. First of all, if there was at least one, then we want to say that AJ is true, I think. Then we want to subtract J minus I times K. So if this is true, oh no, we need to go it backwards, like, right? Oh no, we need to go backwards. It's going to be very slow, I think. I don't know. Okay, we start with this one. So if there are repetitions, we say that it is true. And also if AJ was true, we also make BJ true. Then if this element was true, we subtract one repetition. And here should be star minus repeat of J percent I. But here you need to add one to repeat. Ah, I don't need to do it. Something if J minus I times K is at least 0 and this is true, then I do it. God. Okay, and then I need to swap A and B. And then I need to do this. And here we simply go through how was it done? Let's just copy, I think. Okay, and finally I need to find the maximum number. Good. Three two five one two 22232, and also I think we need to divide S by like 3 or 2. and multiply by 2 as well. Okay, it sounds very peculiar at least, but maybe it works. So let me think. If I didn't... Okay, let's just make some stupid test. Let's make some stupid test. Let's make very, very stupid test. So I want to check. Example, I have 12 vertices. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. No, it doesn't. 10 only. Okay, and I want to get exactly 5 ones and 7 zeros. So then it should be all good. But if I make 6, it should not be all good, and it should say that I failed, right? Not right. Okay, let's say 11, 5, and 11. I am starting to feel too lazy. Okay, let's just submit it. I don't know. Did I save it? Yes, I saved it. Okay, I spent too much time on it. Period. Probably a good idea is to return to problem B, which is very easy. It seems so. Okay, so again, we want to find out whether we can get permutation. We can sort. We can sort the permutation with only the first type of operations, right? What is the second type of operation in terms of the first one operation? In terms of the first operation, we need to swap, make 3 swaps. This one, then, no, this one, then this one, then again this one. We don't like too many swaps. How is it so slow if the time limit is 93 milliseconds? What? Okay. So unfortunately, it's true that the element could be very far away. I understand. I think we need the following thing. We need the fact that there are several segments, and either it is shifted like this, so this element should go here, or this element should go here. So there are several segments of this type. Okay. And we need to find out for each subarray whether it's perfect. How to find that out? So in order to find that out, so first of all, let's find out whether the whole array is perfect. How to do that? It's kind of easy. We just say that we want to find the 1. If 1 is here, we just keep it. So let's assume that we have some perfectly aligned prefix. So we want to find out, so here in the element number I, we want the element I. So if I is here, then we want to see here I plus 1, I plus 2, etc. I plus something. But if I is not here, then we want I to be here, and then we skip. And also it can be that I is here. Then we want to see I plus 4. Then we want to see here some element j, and we want to have here increasing subsequence up to I plus j minus 1, I think. Okay, how to fast find out that this is a good subsequence? We need some beautiful criterion. We want some beautiful criterion. So we have some subsegment. How to find fast that something is wrong with it or something is not wrong with it? Okay, I think can it be that okay, let's say that so if some segment is good, then any subarray of it is also good. Yes, then any subarray of it is also good. So we just want to do something like a segment tree. We want to do it the other way. So we have two good segments. We want to find out whether their concatenation is good. So first of all, we want to find out whether is it true that this maximum is less than this minimum? So if it's true, then it's enough to have this good and they have this good. So the bad case is that the maximum is not less than minimum. Therefore, we will want the maximum of this array to get somehow here. Or, yes, we would like the maximum of this array to go here and the minimum to go to the left. Yeah, but this means that, so this structure that I described here, it's somewhere here. So what do I want to say? I basically want to say that so let's look at the rightmost segment of this array. So either it is just a single element like m, then it's it's not an easy problem. What's happening? It's really not an easy problem, it seems. So can be formulated somewhat in more understandable way. Okay, what about this one? So this is, it is bad, isn't it? Ah, yeah, it is bad. Basically, we don't want to swap 5 and 4. Ah, but how to explain that? Okay, for each element, I want to say where I want to move it to the right and where I want to move it to the left. Maybe. So if the element is greater than the next one, then I want to move it to the right till it gets smaller. So what do I do with it? So what do I want? Maybe it's really a segment tree, but it's an uncanny segment tree. So how do I merge two segments? So I think I want to know the minimum of the segment, the maximum of the segment. What else do I want to know from a segment? I want to know the biggest unsorted. I want to know the first. I want to know whether it's good. I want to know where it's sorted. I want to know the last element till which it is sorted. This is what I want to know. The last element till which it is sorted. And so how do I want to know that? I want to know that in the way, so if I have 1, 2, 3, 4, and then I have 7, 5, 6, for example, then the element should be less than 5, actually. Yeah, the element should be less than 5. So I want to find the first element which is greater than the previous one, and the first element which is smaller than the previous one. The first element which is smaller than the previous one. Okay, I think I just want to know the first unsorted pair. That is what I want. And maybe the last unsorted pair. Mm. Okay, so let's say that first unsorted, last unsorted. What else? Is it enough to merge two segments? So how can I merge two segments? So I need to consider several cases. First of all, if maximum is less than minimum, then it's easy. Secondly, so let's assume that maximum is greater than minimum. Then either I want to move this maximum to the right side, or I want to move minimum to the left side. If I want to move maximum to the right side, I need a couple of things. Firstly, the second maximum is less than minimum of the right segment. Yeah, so it looks like 10, then 3, 4, 5. And then 5 like is greater than is less than like 6 and 7. And secondly, 10 should be less than this number 5 here. It should be less than this number 5 here. Yeah, this 10 should be less than this number 5 here. So when we look at, like, if it looks like 12 and then 11, this means I can move 10 here and then yes. Maybe I simply just need to find all unsorted pairs. Yeah, let's just look at all unsorted pairs. That's so let's look at our array. Let's look at all unsorted pairs. So these are all unsorted pairs. What do I want then? So first of all, these numbers, so if these are all unsorted pairs, then this, for example, is a sorted array. And this is also a sorted array. And this is also a sorted array. So what do I want then? Basically, I want how it looks. How does it look like? So it looks like, for example, 15, then 4, 6, 7, 10, and then, for example, 5. Then why is it bad? It is bad because this number wants to go that way. So actually, in each unsorted pair, this element should be less than this one, I think. So if we have several unsorted pairs, then L of the left pair should be less than R of the right pair. I think that's it. Yeah, I think that's it. So we take the segment. We take all unsorted pairs, and we just ask, is it true that so each pair which is fully in our segment, this should be less than this. And that's it. So basically we don't want both these elements if this is greater than this. Yeah, because this somehow goes to the left, this somehow goes to the right. And if we want both this element to jump around 5, then we want this jump which is far from ideal. Okay, what about the case when it looks like it always should be. Okay, let's just try it. I don't know. So what do? We read the permutation, and we want and we also read several queries. And we want to return vector of bulls. So let's just return this vector of bulls. Okay, what do? We need to read Q. So then we want to find answer like this. We go with P and V will be from ans. We print B yes no. Okay, so let's find all unsorted pairs. Yeah, let's find all unsorted pairs. Is there transitivity? So for example, is it true that if this is bad, then either of these two is bad? So here, let's say that we have A and A, B and B, C and C. So we know that A is bad, so A is less than C, is greater than C. Is it true that then we know that either A is greater than B or B is greater than C? I think we know, because otherwise we know that A is at most B, B is at most B, and B is at most C. And then we know that A is at most C. Okay, there is a transitivity. So let's go for int I from 1 to n. So if pi is greater than pi plus 1, then it is an unsorted pair. And we want to store the previous unsorted pair, right? Yeah, let's store the previous unsorted pair. So we need to say that PR equals previous unsorted pair. Let's just store as number. So we will say that PR equals I, but before that, if PR is at least 0 and PPR is greater than pi plus 1, we want to add to bad pairs. Yeah, we want to store the set of all bad pairs. We say that bad implies back what? PR and I plus 1, I think. So these two elements, it's bad to have both of them. It's bad to have both of them. Yes. Then we want to go through all these PIIs. So I want VBANs for PII query. Quota XY from VM. Let's see. So we want to find out whether there is at least one bad pair between X and Y. So we want to find the first bad pair which is at least X. So we want to find lower bound of bad begin, bad end, and pair, for example, of X and minus 1. Okay, let's find it. So if IT is not bad.end, this means that there is at least one bad pair. So let's also ask, is it true that IT second is strictly less than Y? This is what I want to ask. So is it true that ITY is strictly less than Y? This means that this pair is whole. This whole pair is inside our segment. So basically we want to say that we want to say ans.pushback this. So IT is equal to this, or this is at least this. Good. And return ans. Okay, let's find the answer. Thank you, Visual Studio. Yes, no, 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 no. Yes, yes, no, yes, yes. Okay, makes sense. Okay, now problem D. Wrong answer, test 2. But we don't have test 2. So we have an unfortunate situation of wrong answer. I hate this problem. Why can't I figure it out? Probably again, we just skip it. Let me think. So it could be both ways. So first of all, maybe if there is a bad pair, then still only one is enough. And secondly, maybe if there are no such pairs, then probably it might happen that not only once. Can you move that away? What shit is this? Okay, if we have only these sorts of cycles, so maximum and then sorted, what did I do? Okay. Okay, so if I have only such cycles, right? Then what? So what are the unsorted pairs in this situation? In this situation, the unsorted pairs are this one, this one, this one, this one, and this one. So they should be non-overlapping. So this element should be less than this element. Of course, this is true. Okay, also this element should be less than this element, and this is true. Ah, also this element should be less than this element. And this element should be less than this element. Yeah, all of that is simply... in this case, I also want this element to be less than this element, you know? So this is not enough. So let's consider the case where it's not enough. For example, it's 2, 3, 1. No. 20, 22, 23, 21. And then, for example, ah, 22, 23, 1. Then, for example, 2, 3, 4, 5. That is already very bad. Yes, so this element should be greater than this element already. But how to ban that? How to ban that? Okay, obviously I don't want... So is it true that I just don't want such arrays and such arrays? So both are red flags. So no descending triples and no big 2, small 2. Yeah, and this one, what does it detect? When I have AA, BB, it looks like 4. It looks like 3, for example. 2, 4, 1. This is also a red flag. This is also a red flag. So 3, 1, 4, 2 is also a red flag. So is it true that if I have an unsorted pair, then I want this element to be greater than this one, and this element to be smaller than this one? Is it true always? I don't know. So in this unsorted pair, really this is true. And this is not true. So it's fine if an element is smaller than a lot of elements to the left of it. But this will mean that... So again, if I have an unsorted pair like 4 and 1, this either means that I want to move 1 to the left, and this means that this element should be greater than 4. Or this means that this element should move to the left. And this means that each should be less. So either of these two should be true. So probably let's just say that if this element is greater than... I don't know. I really don't know what to say here. Okay, let's also say that... So if pi plus 1 is greater than pi minus 1. Is smaller. And pi plus 2 is smaller than pi, then bed in place back I minus 1, I plus 2. But also it should hold that I is less than I plus 2. If I is at least 1 and I minus 1, okay, is at least 0, and I plus 2 is less than n. Okay, then I think we will need to sort bed. Okay, let's create some tests which didn't work before this fix. So, for example, let's do like this. For example, let's add a test of type 3, 4, 1, 3, 4, 1, 2, 1, 4, like this. So it will say that it is a perfect thing. However, it will turn out to be non-perfect now. Yes. Oh my gosh. Still no. Okay, another thing that I want to disallow. Basically, yeah, what I don't want. So if I have an unsorted pair, I don't want the fact that I want to move it to the left, to the right a lot, and this to the left a lot. So either this should be greater, this should be smaller than 1, or this should be greater than this. Okay, that makes sense. Also, I want... I don't want it... So this should be just greater than this one, right? I'm not... I did a bad thing. Okay, I needed bed 1 and bed 2, and put this here and this here. And do this and do this. This is the correct approach. And then I even don't need the sorting because it is already sorted. Okay, it's a nice thing to hate. It's a poisonous problem. I don't know what to say. So I checked not everything. So 3, 4, 1, 2, right? But it could also happen that it looks like 2, 4, and then 1, 3. What happens in this case? In this case, I actually just make this swap, then this swap, and then this swap. Well, of course, I can do 2, 4, 3, 1. Then this big swap and then this small swap, but this doesn't make sense a lot. So basically, I want all three inequalities. Like, also check that p I minus 1 is greater. Like this. I don't know. Okay, Is it true that I always detect decreasing triples like this? Yeah, is it true? Somewhere along the way, so let's look at the first decrease. It will be look like something like at least 3 and then at most 2. So there will be something like this. And here we also will have something at least 2 and something at most 1. And we will detect it, yeah, because this is less than this. I really don't know. Let's just skip this problem. Geniuses. I don't know. They just geniuses. N sliders on a one-dimensional track of length m. Each slider occupies exactly 1 unit of space and starts at a distinct position. The sliders are numbered from 1 to n and arranged from left to right. Q operation. So during the operation, we move the ith slider to position x. But if this causes a collision with another slider, that obstructing slider is pushed in the same direction by 1 unit until it is no longer causes a collision. Yes. Yes. Forgotten the order in which the Q operations were applied to recover results, he decided to independently simulate each of the Q factorial possible permutations. For each permutation, define FIP as the final position of the ith slider after applying the operations in the order specified by P. Your task is to compute the sum of FIP over all Q factorial permutations of the operations. How to do that? And of 5,000. Okay, 5,000 is not that crazy because this means that it can at least can be done in square time. Okay, let's look at the slider. So we have some slider, number I. So let's find out how many yeah, well, actually, each operation just says become equal to I, or become at most I, or become at least I. So in some order. So this there are just these three types of operations: become equal to I, become at most I, and become at least I. That's it. These three types of operations, and we need to find out how many ways of doing that are there. Okay. Okay, that makes sense. Let's take some slider. So let's iterate over all sliders and over all possible destinations. So I ask in how many permutations the ith slider gets to the jth position. Ith slider gets to the jth position. Okay. In order to do that, I want to find out what was the last operation that moved this slider. Of course, it was a j operation. It was operation which used some number j. Therefore, so how did it look like? So firstly, there were several operations that somehow made the position. Okay, so let's just look at the last j operation. That's it. That's what I want to say. Let's look at the last operation in which j is featured. So it's somewhere here. So after that, j is not featured, and moreover, it only says become at most something which is greater than j, or become at least something which is less than j. That's it. So some operations of this type. Basically, all these operations can be ignored. So let's just remove them. Let's put them in the end in this sequence. So the last operation which does something is operation with exactly number j, and this is the last operation. Okay, so this last operation. So if it is equal j, then it's easy. Equal I, then it's easy. Equal j. So also it could be operation become at most j, in which case this should be something that makes the number at least j. So this should be something that makes the number at least j. So how to make the number at least j? We just want to consider the last operation which says equal or at most. We take the last operation which says equal or at most. So, and after that, there should be an operation which says at least. It actually doesn't matter which exactly, because we removed all operations which are too small. Okay, so basically, I have 6 types of operations. Let's say that I have 6 types of operations. I have 8 types of operations. I have 8 types of operations. Let's list them. So make I, make greater than I, greater or equal than j, where j is at least is greater than I. Make at most j where j is less than I. Make equal to j where j is greater than I. Make equal to j where j is less than I. 6 types of operations, I think. Yeah, and the 6th type is just basically skip. Oops. Basically skip. Okay, these are the operations that we need. And we want, based on these 6 numbers, find the answer. I don't see. Okay. We want to, based on these 6 numbers, find the answer. So first of all, skip doesn't matter. So we want to find these numbers. Let's say that the sum of these numbers is k. Then after that, I want to multiply by k plus 1, k plus 2, etc. times n. So this is what I do. So this is what the skip does. So now let's forget about the skip operation. Now I want to choose the last operation. So let's say that it is A, B, C, D, E. So the first case is last operation was A. So I choose the last operation in A possible ways. Okay. If I chose it to be A, then it's just basically all the other operations in any order. So a minus 1 plus b plus c plus d plus e factorial. Any of these operations, but the last one was a. Okay, this is easy. The next thing is b. Not b, but 8 types of operations. Because there is also at least I and at most I. Let's call them somehow. Okay, this was an error. Let's see, at least I, at most I. So this is B, C, D, E, F, and G. So let's rewrite. So it's A times A minus 1 plus B. Let's call it like K minus 1. So the sum of all numbers, these except skips, is K. So this number of ways. Okay, now let's say that the last operation was at least I, B. Then, before that, I want to order the operations in the way that makes the number at least at least what? I want the last operation to be make it at least I, at most I. So I want either C or I now want to. So I now let me think. So I want the last operation. Why doesn't it work? I want the last operation to make it. For some reason it stopped working. It started working. So since the last operation says at least I, then this thing should make it at most I. So this thing should make it at most I. How many ways to make it at most I? So I want to consider the last operation, which is substantial operation, which changes this status. Which operation changed this status? So operation at least I does not change this status. But the rest of operations change the status. So let's consider the last substantial operation. So how do I do it? Okay, so I'm okay with any equals I. The last operation could be equals I. The last operation could be B, but we skip it because it is not substantial in this case. So, okay, C is also very good. So make it at least J where J make it at least J. Okay, let's just order everything except B, and then we will put these B minus 1 operations at last. Okay, A plus C, then this does not help to make us at most I, this helps, and G helps. Okay, these operations are good. Okay, after that, the rest of substantial operations should be ordered. The number of substantial operations is K minus B, because these are all not substantial operations, and also minus 1, so this factorial. And then I want to order the substantial operations. How to order them? I need to multiply. So these, the number of operations here is K. Let's just forget about B. So A plus C plus E plus G times K minus B minus 1 factorial. Wait, what? K times this? Ah, it should be K plus 1. Okay. So this, if we multiply by skip, it probably becomes equal to A times N factorial over K. Something like this. Okay, so let's consider non-substantial operations. It's A plus C plus E plus G times the factorial of these operations. Okay, this makes the answer at most I in the end. K minus B factorial. Then we want to add the last B operations. How do we add them? We consider all K factorial orders No, how do we do it? So first of all, we add b minus 1 elements in any order. So if we already have k minus b elements, then the next one can be added in k minus b plus 1 ways, etc. K minus b plus b minus 1. Yes. And then the last element should be definitely in the end. But then I need to choose which of them I will put in the end. So something like this. Okay, and then I multiply it by skip. So I need to multiply it in the end by n factorial over k factorial. So let's calculate what it looks like. It looks like a plus c plus e plus g times k minus 1 factorial over k minus b, and then times b. And then we also multiply it by this thing, and so we get a plus c plus e plus g times n factorial times b over k minus b times k. Okay. Oh my god. So we need to read what? T, then N and Q, NMQ. Then we read the vector A of size N. Oh no, the number of sliders. Oh no. Ah, it doesn't matter. Not. Okay, the problem just became harder, but we can merge, we can squish the coordinates. Okay. What is M? Ah, M is the last element. I am R. Okay, let's go. So how do I let it go? So we need to iterate over all sliders. So my aim is to find ans I here. So how do I do it? So first of all, I need to find out, is it true that I never move this slider? So let's just say that for each other slider, I want to find out what it does, basically. What does this slider do? What does this slider do? Ah, no, it's not that easy. It's not that easy. Because oh shit, there are too many things that could happen, right? So there are 5,000 times 5. No, there are basically 5,000 positions, right? Yeah, there are 5,000 positions. No, it's not the end of the world. Yeah, for each pair, let's say what it does. So let's say that we have vi equal, less equal, and greater than equal. And also int skip. Then let's go through this array. And what do we say? We say the following thing. We say the following thing. So we move the xth slider to the yth position. So if x is equal to I, then we just move it to the ith position. So we say that eq dot push back y. The second case is that so the next thing is x is at most I. So x is less than I, then what? Then after we move it, it gets at least y plus I minus x. Also plus I minus x, right? So if x is less than I, If x is greater than I, yeah, something like this. Okay. Other skip operations. No operation is a skip one, right? Yeah, no operation seems to be the skip one. Okay, also we know that okay, let's say the following thing. So the first position of this slider is AI. So let's answer the question, do we ignore AI or not? So let's say that so for int I from EQ. So if I is not equal from let's say J, not I, or even Y. So if Y is not equal to AI, then let's say not ignore AI. Plus this. Else if Y equals AI and no, not Y equals AI. Let's say like this. So if Y is less or equal than AI, then also not ignore AI plus plus. If Y is greater than this. And here, if it is smaller. So if we got that we have to ignore, then we simply can find the answer. How do we find the answer? We just say that answer I is equal to product. What is a modulus? Modulus is this one. So we say that it is simply the product of AI and factorial. We need to find out how the factorials are counted. M is this number. Yeah, it seems like it's fine. I can use modulus M. Factorial of P modulo M, modulo M. No, not P, but N factorial. Okay, good. So now I cannot ignore... I can ignore AI. So AI does not exist. Then my answer depends on this number EQ, LQ, GQ. So now I need to sort them. So let's say that I have EQI index. So this is not considered indices. LQI equals 0 and GQI equals 0. So while EQI is less than CZ-EQ, or LQI is less than CZ-LQ, or GQI is less than CZ-GQ, I do something. In the end, I will get the ans I correct number. So these are my three indices. So I want to find the minimum number, the number which we are going to get. So I want to find the number of ways. I want to find the number which is equal to n, but so let's say that if EQI is less than CZEQ, then number is equal to minimum of number and EQI, and the same with GQ and LQ. Okay, I have my number, and I want to find the number of ways. When I find the number of ways, I can say that ans I is sum of ans I and product of number of ways to get a number and the number itself, modulo n. Good. So I already know the number, so I just want to know the number of ways. So we know that the number of ways is sum of three numbers, A, B, and C. So we want to find them all. So I will say that int ways A equals 0, ways B equals 0, and ways C equals 0. And in the end, I will say that ways equals sum of ways A and sum of ways B and ways C modulo M modulo M. Good. Okay, now let's find these three numbers. So ways A. Ways A. For that I need to find all these numbers. So I want to find out. Okay, let me think. So, do I have these numbers available? Okay, let's call them. Okay. So when I will find them, when I find them, I will be able to say that n is equal to n minus na minus nb minus nc minus nd minus ne minus nf minus ng. Crazy. Okay, how to find them? Okay, first of all, na. How to find na? So let's say while EGI is less than CZEQ and EQI equals number, I say plus plus EGI and plus plus NA, because NA is exactly how many times this is exactly a number, right? EQI. This is exactly my number. After that, make exactly j where j is greater than I is NF. So I will be able to say that NF is all equalizations minus EQI. And basically, G is EQI. Okay, this is about equal numbers. What else? Then the operations make at least. So there are operations which ask to make at least I. Okay, we can also count them. While make at least this and this and this, and make at least I is B. And in the end, all the remaining operations, they say make at least j where j is greater than I. And they called nd. So we say nd equals z gq minus gqi. And in similar manner, these operations where j is less than I, it's ne equal lqi. And then again, while this is true, we add it to nc. Good. So nc, ne, nd, nb, nf, ng, na. All 7 numbers are calculated here. And also k. Great. Now we need to find all these ways. So what is ways A? As we said, we need to choose A multiplied by n factorial and divide by k. Just this, yes. This product of A and product of factorial n. Okay, let's call fact inverse something. Let's say inf factinv and n. So how do we find factinv? For that, so if n is at most 1, return n, and else we return product of factorial of n minus 1 and inverse factorial of n. This is factinv. And we use it to find factinv of k. But what if k is equal to 0? Ah, it is impossible. I think it's possible. So k is not 0. Ah, modulo m, modulo m. What? Ah, na. Okay, then ways b. What is ways b? We need to multiply this thing. A plus c plus e plus g. Okay, this is a plus c plus e plus g. Then we multiply it by n factorial and by b. Okay, and then we divide it all by the product of k minus b and k. So we need to take in fact of k minus b and k. Okay, and YC is calculated similarly, but so first of all, instead of B, it is C everywhere. Instead of C, it is B. And also instead of E and G, I need D and F, I think. Good. So I think that's it. It just needs to be without bugs, and I won. Okay, not good. Very not good. Q permutations. Still not it. Where do I use N actually? Probably here. Also, why are numbers so big? Ah, numbers could be so big. Okay, let's make some very easy test. So I have two sliders up to 10. I have 0 operations, and initially they are at 4 and 6. So I want to see 4 and 6. That's it. Yes, it's easy. So now let's make one operation, which says that first slider goes to 4. Still 4 and 6. Now it goes to 5. Now it's 0 for some reason. Let's see why it is 0. Okay, first slider. Okay, let's look at the second slider first of all. Okay, let's again look at the 0 slider. Okay, we cannot ignore it. And then we sort all of these guys. So number is now 5. Okay, number 5 is okay. So NA is 1. Ah, there are also a lot of skips. Ah, they are automatic. Okay, the skips are counted automatically. So base A is product of NA times... Ah, why is K 0? No, it is wrong because I needed to write plus in each of these places. Ten six now. Why 10 6? Ah, because number of ways is calculated incorrectly. Okay, because here it should be q factorial, right? And here it should be q factorial, and here it should be q factorial. Okay, once more. 5 6. Now let's make it 4. And let's see what it says. 18 to 89, 35, 41, 47, 3, yes. Oh, this should be 6, but it's instead some strange number. Why? Okay, let's see why it is such a strange number. So actually nobody moves the first slider. Why? Is less than AI? I is 0. And Y is what? What is Y? This is Y, right? Maybe I somewhere use I where I shouldn't. Ah, no, I don't do it. So it's product of AI, which is 1, and factorial of Q modulo M. So each factorial of Q modulo. What happened? So first of all, it's factorial. Ah, It's 2 million. No, 2 million is enough. Why inf became true? Why inf became true? What hell? Ah, because you don't write factor. Ah, we don't write factorial modulus. Makes sense. Makes a huge amount of sense. Okay. So I spent like hour, like yeah, 1 hour on this problem. Blazing fast ores. What's happening here? So first of all, skip is something made up. Maybe this is wrong, really. So again, ans I is equal to product of AI and factorial of q modulo m. And continue. And this is if we can ignore and it should be called ignore AI. So we can ignore AI if at some moment y is not equal to AI. We also can ignore it if there is a number which is greater or it is smaller. Okay, let's try again. We consider the last operation. Okay, let's rewrite, for example, again, the first case. So the last operation is equal. So again, there are these numbers in total they are k, and we say that first of all, let's say that q minus k operations they don't matter. We can apply them in any order, It doesn't matter what we do. Actually, I understood what's wrong. I understood what's wrong. And what's wrong is that it can be that we made the number at most I, but before that we cannot make it at least I. Okay, let's rewrite it a little bit another way. So let's say bool automatically okay, no, what? Okay, the last operation is to make number at least I. Okay, the last operation is to make the number at least I. So what is the problem basically? The problem basically is that we make the number at least initially it is AI. Okay, let's just I remember about the problem. Let's just fix the other problems if they are present. So there are q minus k skipped operations. We just do it in any order. What does it mean to make them in any order? It means that we take our operations and then we apply them, these operations, in any order that we want. So since there are k operations here, then we multiply by k plus 1, k plus 2, etc. q. This means that it is just answer times q factorial divided by k factorial. Good. Then let's look at how we can manage this one, non-skip operations. So first of all, we can make the equal operation the last one. There are exactly a ways to do that. Then the rest of the operations, there are k minus 1 operations there, and we need to make them in any order, which is k minus 1 factorial. So if we multiply that, we get a times q factorial divided by k. So a times q factorial divided by k. A multiplied by q factorial and divided by k. Good. Also k could be equal to 0, but that is impossible. That is impossible, yes. Okay, then the second thing is to firstly make it at least. So the last operation we say is make it at least I. And this thing we make it at most I. Good. So what do we do? The last operation can be chosen b possible ways. Then the rest of these b operations can be applied at any moment. So these b minus 1 operations can be applied at any moments except the last one. So we take these, we take this q, k minus 1 minus, k minus b operations actually. Here we have k minus b operations, and we insert in any order these b minus 1 operations, And the number of ways to do that is k minus b plus 1, k minus b plus 2, and finally when it is exactly k minus 2, k minus 1, right? So it is b times k minus 1 factorial divided by k minus b factorial. Then in the end we will multiply it by a q factorial over k factorial, and we will get k minus b factorial, k, and here we get q factorial. Okay, so we need to find the number of ways to get here the number at most I without b operations, so only a, c, d, e, f, g. In order to do that, we notice that. So what do we notice? Let's draw with blue. So we know that this is definitely making it at most I, so this is good. This is good, it definitely makes it at most I. This is good. This is ignored. What about the rest ones? So this one definitely makes it greater than I. Okay. This one definitely makes it greater than I. Yes? Does it make it definitely greater than... it makes it at most I, so this is good. This definitely makes it greater than I, so this is bad, and this is good. So I need A, C, E, and G, and not D and F. So what do I do? So I have K minus B operations possible here. So I need to choose the last one in A plus C plus E plus G ways. Then I need to order the rest of the operations. How many operations are there? There are k minus b minus 1 possible operations, and I just take their factorial. So I get a plus e plus a plus c plus e plus g times k minus b minus 1 factorial. That's it. However, if A, C, D, E, F, and G are all zeros, that is, if k equals b, then I cannot do anything, and I need to skip this step. And instead of that, I need to look at AI. Okay, so what do I do? So if k equals b, instead of that, let's say that I have not ways b, ways c. I also have prefix b and prefix c. Okay, so first of all, I need to calculate prefix b. So if k equals b, then prefix b is basically, so how many ways are there to order these k minus b elements, of which there are none actually? So what? Well, it should be 1. But then where is my b? So in the end, so what? k minus b factorial. So this is 1. So this is 1. So if I only have operations of type at b, then what do I want? I want simply b factorial here. Well, I basically want any. I basically want q factorial. K equals b. So this will cancel out. So I just want the blue part to be 1. Okay, then prefix b equals the fact. Okay, I don't want to make it prefix b of prefix c. So k equals b. It means that I want to say that always b is simply q factorial. So it is q factorial. It is equal to q factorial if the initial number was at most I. Yes, if it was at most I, then I can make it exactly I. So if it was at most this, then q factorial, else nothing. And same way here, so if k equals nc, then way c is ai is at least number. Else I do this crazy thing. I think I need some tests to test this. How do I test this? Ah, I think I can make it. One seven, I think. And also, we want to consider the case where it is 4, 9, for example. Probably, I don't know. Ah, so I spent a lot of minutes. And it still can be a wrong answer, actually. But it is not, probably. Ah! The second operation can be applied at most once. Oh my god. Okay, let's think again about this great problem. Okay, the round is unrated. Well, let's test past. Now let's solve this problem B. Now that we know that the operation B, the operation 2 can only be applied at most once. What? Does it make the problem easier? I don't understand it. Let's look at all our... What? Is it just now about 3 to 1 subset? Yes? No? What about 3, 4, 1, 2? So I can do it in 4 operations. What if I make this swap? So I can make it in 4 swaps. So it is simply about there being this pattern, and that's it? About pattern 3 to 1? Okay, how to check that? How to check about this pattern? So we have several segments. We need to find out where there is a decreasing 3 pattern. How to do that? My brain stopped working, but let's try nevertheless. So we have a segment. What do we do? So if there is no such pattern 3 to 1, what does it mean? Does it mean that it is just an increase in subsequence and then another increase in subsequence? Or does it not mean this? So let's take the minimum number. Minimum number here. It can be covered with 2 increasing subsequences. That is the case. So they may interlope, intervene, intertwine. So how to check whether we have this pattern So as I said, this is simply equivalent Okay, assume that we have this pattern, right? First of all, let's consider the smallest one, the smallest, the smallest by inclusion. Okay, so there is this pattern somewhere. Okay, if this number is greater than 3, and moreover, if it is greater than 2, or I mean, so all numbers here are less than 2 actually, because if they are greater than 2, they are all less than 2, because if at least one is greater than 2, then still we get a smaller pattern. So they all are smaller than 2. Also, they are sorted, because if they are not sorted, then there are two elements which are less one another. And then 3, this and this is also a decreasing subsequence. So 3, then sorted numbers which are still less than 2. Then 2. But is it true that they are greater than 1? Okay, they are less than 2. By similar logic, we know that all these numbers are greater than 2. And then 1. So we know that it is just some big number, then sorted sequence, and then smaller number. And this sequence happens to be intersecting the segment 1, 3. How to detect that? We can simply say that we consider this unsorted pair, then all of this is sorted, and then we consider this unsorted pair. And what do we want? We want 3 to be greater than 1, but also we want some smaller number in between. How can it not happen? It can happen that it is 3, then 0, for example, then 5, then 1. What do we do in this case? Or let's just write it 3, 1, 4, 2. How do we not detect that? So we are not interested in this. But if they're 2.5, then we are interested. Hmm. So this thing can be ignored, basically. This thing can be ignored. So what do we do then? I don't understand. I really don't understand. It should be very easy. It should be very easy. So how to check whether the segment has 3 to 1 pattern as a subsequence? So let's consider the biggest sorted subsequence. Then there is something smaller. Okay, first of all, if it is sorted, then it is easier. Okay. Okay, no. No, 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 no. No, it should look like this. It should look like this. The maximum of the segment, then the minimum of the segment. Even not an exactly minimum, just some number, some smaller number. And between them, there is some increasing subsequence sequence that intersects this rectangle. This is what I need. Some big number, some smaller number. So there are two conditions. Okay, let's try and do it. Just take one of the previous solutions and change it. So this is a good part. This is a good part. Yeah, this is a good part, but here we want to say the following thing. Here we also want to check whether it's true. So we have PR, this is a big number. Then we have PR plus 1, but this is a small number. Then it grows, and then it again at moment I is big, and at moment I plus 1 is small. So we want to check whether there is at least one number which is between I plus 1 and PR. So we want to find it. Let's just find it. Lower bound between p dot begin plus PR plus 1 and p dot begin plus I plus 1. And we want to find the number which is at least pi plus 1. So if it equals p dot begin plus this, if it is not equal to this. So we found some element. And if this element is less than ppr, only then we do this thing. Okay, yes, no, 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 no. Yes, yes, no, yes, yes. Okay, maybe this will work. I'm not sure. I'm not sure. Is it a good detection? You just ruined my contest. I don't know. Okay, now at least it makes sense. All of this started making sense. Okay, very fast explanations of problems. Let's try and do it. So problem A. The manager of a cake shop. So we have two numbers, and we have the following operations. One of the number, which is even, is halved, and this half is added to then another number. And that's it. So we have two numbers, starting with two equal numbers, and we do the following. We take one of the numbers, half it, and add this half to the other number, and to the other number, yes. And we can do it any number of times in any order, and we get the final situation. We need to find out the shortest sequence of moves that could end up like this. So this is the classical problem on the idea of reversal. So let's just reverse the process in time. Yeah, we have two numbers. We have two numbers, A and B, and they became A over 2 and B plus A over 2. What do we know about these numbers? So if they are x and y, basically we always know that y should be at least x and even greater than x. Yeah, at any moment of time, both numbers are positive integers. And after this operation, they are also positive integers. This means that b is greater than 0, and this means that it should be greater than this. So at any moment except the very first moment, y should be greater than x. Yeah, there also were the possibility of another operation, which looks like a plus b over 2 and b over 2. But in this case, this sign would hold. And in this case, this sign holds. So basically, at any moment, any situation can be undone. So we can undo one step exactly this way or this way. So we can undo, in case x is less than y, this operation, green one. And if x is greater than y, then this operation. So let's analyze how do we undo one operation. So this operation, if we want to undo it, we need to double the first number and subtract the first number from the second number. So it looks like this. And if x is greater than y, then vice versa, x minus y and 2y. And also, if x equals then y, then it is just starting position. Therefore, at any moment, there is exactly one thing that we can do. If the numbers are equal, we need to subtract the smallest from the biggest, the smaller one from the bigger one. If the numbers are equal, then this is always a starting position. So you just undo them until you get two equal numbers, and it turns out that you will always do, because the sum a plus b is a power of 2, and because after each operation, the power of 2, like GCD of a and 2 to the power k plus 1, it always grows. Either a is doubled and it grew, or y is doubled, and that means that x minus y, that number, which is just equal to 2 to the k plus 1 minus 2y, it is also the number of 2's in its prime decomposition also increased. That means that this GCD always grows, so after at most k operations, you will get 2 to the k and 2 to the k. Okay, problem B. What do we get here? Problem B. Okay, you will read it in the editorial, actually. So I claim that in the editorial you will find the I need first to explain the statement of the problem. So in this problem we have an array B of length m. There are two types of operations. We can swap two adjacent elements, or we can swap two elements which stand which like skip one number and then swap two around it. But you can only perform operation two once. Then it is two numbers are defined. F of B is how many operations you need to sort the array using both operations, but operation 2 only once at most. And G of B is only first operation. Then the array B is called perfect if these numbers are equal, and we need to fast detect whether an array is perfect. So in the editorial, you will find the following great fact, that an array is perfect if and only if it does not contain 3-to-1 subsequence pattern. What is 3-to-1 subsequence pattern? It is simply three indices I, j, k, such that I is less than j is less than k, but ai is greater than aj and aj is greater than ak. Such thing is called 3-to-1 subsequence pattern. And actually, for some reason, the array is perfect if and only if there are no 3-to-1 subsequence pattern. In one way, it is very easy. If you have 3-to-1 subsequence pattern, then you can speed up your sorting, but by simply using the bubble sort, but not swapping 3-2 and 2-1 for as long as possible. And at some moment, they will be like this. So you do all operations just. Basically, you can sort this subarray and you can sort this subarray. And at some moment, you will have 2, something greater than 2, and something smaller than 2. And then you can swap these two elements and you decrease the number of inversions by 3. Yeah, you decrease the number of inversions by 3. And this definitely speeds up the process, because during the bubble sort, you only decrease the number of inversions by 1. And here we were able to decrease it by 3. And the other swaps still decrease by 1. So we have a discount of 2 in operations, and that means that f of g is not equal to f of p is not equal to g of p. The other way around, you will read it in the editorial, and maybe it's not very clear, but it's maybe intuitive. So you just want to find out, so you're given some permutation, you're given several segments of it, and you need to find out whether they have or have not a 3-to-1 subsequence pattern. How to find out whether you have a 3-to-1 subsequence pattern? Well, in order to do that, let's consider the smallest by inclusion 3-to-1 subsequence pattern. What is the smallest by inclusion? This means that it is a segment where this element is the part of this pattern, this element is also part of this pattern, and also there is some number in between. They form a decreasing subsequence of length 3, And there is no smaller subsegment which still has 3-to-1 subsequence pattern. So if these things hold, then this is called a smallest by inclusion 3-to-1 subsequence pattern. So let's look at the smallest one by inclusion. So I claim several things. So first of all, this part is smaller than 3. Smaller or equal, but since the initial array is a permutation, all numbers are distinct, so we can assume that all numbers are different. So I claim that all these numbers are less than 3, because if there is some bigger number than 3, then these 3 numbers form a 3-to-1 pattern, which is smaller strictly. So there are no such numbers which are greater than 3. So all these numbers are smaller than 3. We know that. The next thing is that they are sorted, so they are increasing. They are increasing because if there is a decreasing pair like this, then 3, these and these numbers, they are forming 3-to-1 subsequence pattern. So this is a sorted subarray. And also I claim that all these numbers are even less than 2. Because if at least one of them is at least 2, then 3, this number, and 2 form a subsequence pattern. So therefore, this is a sorted sequence which is less than 2. This means that this is a sorted sequence with this element 2. In the same way, you can prove that this is a sorted sequence. And that means that all these numbers are some sorted sequence. So 3, then some sorted sequence, then 1. Okay? 3, then some sorted sequence, and then 1. Okay, how to detect such a thing? I claim that you can 3, some sorted sequence which contains a number between 1 and 3, and then 1. What I claim how to find such a pattern? I claim that this should be an inversion. So this is an inversion which is adjacent inversion, meaning that there are 2 elements AI. These are 2 elements AI and AI plus 1, which are in wrong order. This is called adjacent inversion. So this is always an adjacent inversion, and this is also an adjacent inversion. And between these 2 inversions, there are no other inversions because this part is sorted. So you need to detect whether in your subsegment there are 2 adjacent inversions between which there are no other inversions, and check that here you have an element which is between this and this. That's it. So you just need to check whether in this sorted array you can find an element which is between this and this. And if you cannot find them, then you just skip this pair. And this pair is fine. So let's just store all So let's just call this pair bad if there is a number between A and B. So there is number C, which is less than B, but greater than B, but less than A. So such pair of inversions with number between them is called bad pair. So we need to detect all bad pairs. How to detect a bad pair? You just find all adjacent inversions. You consider all pairs of 2 consecutive adjacent inversions. And for example, with STD vector lower bound, you find the smallest number, which is at least b in this part, and you check that it is at most a. So minimum x such that x is at least b should be at most a in this segment. And this minimum can be found with lower bound in algorithm. Okay, with binary search, I mean. So you can find all pairs of consecutive adjacent inversions. Then you just put all such pairs in a set. So let's take this and this index. So these are pairs x and y, and we'll put them in a set or in a sorted vector. Doesn't matter much. So we put this pair in the set. So there will be a lot of pairs. So how to fast check that some segment is bad? You need to find out whether there is a pair which is fully inside this segment. Notice that these pairs are monotonic by the first coordinate and by the second coordinate. That means that you need to find the first pair whose x lies in this segment and then check out the yi. So you need to find the minimum I such that xi is at least L. And you need to check that yi prime is at most R. So this is what you need to check. This can be done in logarithmic time, so the total number of operations is q log n. And before that, maybe n log n for a lot of binary searches. Actually not. Yeah, maybe n log n, I'm not sure. Maybe just O. Something like n log n, I'm not sure. Okay, problem C. Okay, in problem C, it's an interesting problem. So in this problem, you are given several zeros and several ones. You know how many zeros and you know how many ones. Also, you know that you have a tree on n vertices. And you want to put in each vertex one of these digits. Yeah, there. You just distribute all the digits between the vertices of the tree. After that, you take all leaves of your tree and look at the biggest common subsequences of all such strings. And you want to find the maximum possible number that you can get. How to solve this problem? First of all, you can notice that if the answer is k, then basically the first k numbers should be equal to this common subsequence. Why is that? That is quite easy to understand. Or is it? So how to prove that? So let's just, for each blue path, let's circle the vertex which is used in the biggest common subsequence. Yes? So let's say that the biggest common subsequence is of length t. Yes? It has length t. Let's just, on each blue path, from the root to the leaf, circle all the vertices which are used in this T subsequence. I want to prove that we can assume that the only vertices that we circle are the top T layers of this tree. So what do I mean by layers? By layers, I mean the distance from the root. So this is the layer 0. This is usually called height. This is height 1. This is height 2. This is height, for example, t minus 1. And I want to claim that you only need to circle the vertices of these T top layers. How to prove that? Assume that there is at least one path in which at least one of these vertices is not circled. Let's consider the top, the uppermost of such vertices. What do I mean by uppermost? I mean that there is a leaf L. There is a leaf L. There is a path from R to L, which I call usually a blue path. So R is a root. Then there is a blue path. Then there is a leaf. There is a vertex in layer number H, which is not circled, but all vertices from all the smaller layers are always circled. Okay? They are always circled. So in each blue path, the first H from 0 to H minus 1, the first H elements in these common subsequences are always the first H vertices. But in this concrete path, for some reason, we took another vertex as the Hth vertex, not H plus first vertex, not this one. Okay, I claim that we can assume that we can take this vertex and circle this instead of this one. There are two cases. The first case is that here we have 1 and here we also have 1. Then we can just move the circle from this vertex to this vertex. We can just remove this circle and add this circle, and that is easy. So if there are two equal digits, then we can just move this circle. The second case is a little bit harder, and this is the case when there are two different digits. Okay, then I claim that actually this vertex is not used in any of the blue paths, so it is never circled. Why is it never circled? Actually, it's not that easy, as I was previously saying to you, because it's just not easy. Fortunately, it's just not that very easy, as I was saying. It is not that easy as I was saying to you. Okay, let's try, but I will explain to you what is skipped. So I claim that in any other blue path, this vertex is not circled. Yeah, because either this path diverges from this path earlier, or it diverges later, at some later moment. But in this case, if this is circled, then the hth element of the string should be 0, because in this blue path, it was 0 here, right? Because all these are always circled. However, in this blue path, the H element which is circled is 1. So we see here that SH is 1. So the same common subsequence is 0 in one place and 1 in the other place. This is a contradiction. So therefore, basically this vertex is never circled. Now, if we were having unlimited supply of zeros and ones, we could simply put here 1. And that just say that we move the circle from this vertex to this vertex. However, that is not that easy, unfortunately, because when we do that, so we need to get this one from some other place. We need to get this one, and we cannot get it. So I will maybe skip it. You can read in the editorial, but actually it's easy to prove that you maybe can swap this 1 with some 0 from other place. I know where we can get it. I think I know where we can get it. So assume that it is 0 here, right? Let's just take all blue paths on which this vertex lies. On each of them, this vertex is not circled. And on each of them, let's make it circled. Yes? So we take the next circle on this path. There is also always 1 in this circle. We remove this circle always and instead put it here. Now this vertex is always circled. It's fine. No, it's not fine. Now this vertex is always circled. However, unfortunately, it is now 0 and we need 1. It's written here that we need 1 and it is here 0, which will be bad because at some other path, hth element might be 1. And this will be not as common subsequence. But notice that actually when we did that, we released one of the ones. So let's consider the top one in the subtree of this vertex. The most shallow one in this subtree. I claim that it is not circled, because if it was circled, then the circle should have moved to this vertex. And if it didn't, then there was a more shallow one as its ancestor, which also had 1, and this circle was moved. But we consider the shallowest one in this subtree. So the shallowest one in this subtree is not used now in any circles, and we can just swap and put here 0 and put here 1. Something like this. Okay, so now the problem is like this. We have several leaves. We want to find the maximum number h such that we can take the 0th layer, the first layer, or let's call it L, etc., and L minus first layer, and cover each layer in the same digit. So for example, this layer is only in zeros, this layer is only in ones, etc. This layer, for example, also in zeros. This is a classical backpack problem, or knapsack problem, where you have sizes as 0, etc., as L minus 1, and you need to color some of these numbers blue and some of them red, such that the sum of blue numbers is at most, I don't know, k, and the sum of the red number is at most red numbers is at most n minus k. This is a knapsack problem. You can solve it in sum of size times basically squared. How to solve it in this time? Okay, so again, the problem. You have several numbers. You need to color them in two colors, red and blue, such that the sum of blue numbers is at most k, and the sum of red numbers is at most n minus k. How to do that? You can do it in square time. You can do it in square time by simply creating a vector of bools of size sum of si, which says whether you can reach such sum or not. Okay? Initially, you did not use any of such numbers, so you can only have true at the 0th element and zeros at all the other elements. Then let's add elements one by one. When you add some element of weight x, you need to do the following thing. So if ai was equal to true, now you say that ai plus x is also will be equal to true. However, if x is equal, for example, to 1, you will get the following thing. You ask, is it thing true for I equals 0? Yes, it is. Then ai plus x will also be true, and you put 1 here. Now you consider this element, and again you see that it is true, so this should be true, and you put 1 here. And that way you will fill the whole array with 1s. Basically, you made the following error. You said that you have an unlimited supply of such x's, whereas you only have one element. One try to use this element. To fix that, you only need to do it in the reverse order. So you start with I equals sum of size, and then you go to 0, and then you apply the separation. That way, if you change some element, it is to the right of all the next elements, so it will not affect your computations. So you can do it in this time. There is a technique to do it in sum of si's to the power 3/2, which I used. It is an application of square root decomposition. You still have this array, but you treat the different elements differently. So let's say that sum of si's is called s, and let's look at elements which are smaller than square root of s and which are greater than square root of s. So the elements which are greater than square root of s, you just consider them in the same manner as I just have explained. So one element is maintained, not maintained, how it's called, processed in O of s time, and there are at most square root of s such elements, because if they were greater than this many such elements, then their sum would be greater than square root of s times square root of s, so it would be greater than s. No, it is impossible. There are at most square root of s such elements, and you process all of them in O of s time. Now about this one. Such elements, the number of such elements can be very big. However, the values of such elements can only be from this set. They can be 1, 2, 3, etc. square root of s. No more than that. So if we could consider all elements equal to 4 at once in one batch, so maybe there are 400 4s, but if we consider them in one traversal, then it's still O of s times square root of s. And the total asymptotics will be O of s to the power 1.5. Well, you can do it. It's similar to this technique, but you remember that you can take the element x at most 400 times. You can watch in the contest how I did it, but basically just you count the number of such elements, and then you somehow process with sliding window for each element whether you saw in this arithmetic progression at least one element equal to true. And if you saw, you update it, and then you move the sliding window by adding this element to the sliding window and canceling this one. Quite standard. Okay, so this asymptotics. And with this asymptotics, you can solve both versions of the problem. With the slower asymptotics of O of s squared, you can only solve C1. The last thing that I wanted to explain is how to find this number L. Yeah, because I said you can check whether number L works. I need to explain two things. First of all, how to find number L. Yeah? Basically, you take the shallowest leaf. Notice that if the height of shallowest leaf equals h, then you never are able to get the answer greater than h plus 1. Yeah, because for this leaf, the whole sequence is a0, a1, etc., ah. You cannot get more than that. So you can have at most h plus 1 elements. Okay? You can have at most h plus 1 elements. So you will try L equals exactly h plus 1. I claim that it is enough, because if the knapsack problem solution said to you that it is impossible for L equals h plus 1, then it is always possible for L equals h. This is also one very common idea. You have several elements, a1, a2, etc., an. You want to divide them into two piles where the first pile is at most p and the second pile is at most q, and the total sum of the elements is equal to p plus q, for example. I claim that you always can do this division except one element. So you can make three piles. The first pile is at most p, the second pile is at most q, and the third pile at most one element. You can always do that. How to do that? Simply out of each element make a stick of this length. So for example, this element a1 becomes a stick of length a1. Then a2 becomes a stick of length a2. You continue this process and you get a stick of total length p plus q. Now simply measure p from the beginning of this segment and break this glued stick here. There are two cases. Either this place is exactly between two sticks, then you divided all elements into two piles, one of size p and the other one of size q. The other case is that this was some single stick and you broke it. Then this stick goes into this pile. So with very easy greedy algorithm, you can always get answer h. So the question is, can you get the answer h plus 1? To do that, you just run this instance of knapsack problem exactly once, and you can solve the problem. The second thing that I wanted to discuss is this. What to do with this great array. So as I said, during the process of this algorithm, you have a Boolean array and you update it with each of the elements. In the end, you will have a big Boolean array with trues and falses. What to do with it? This is the question. So, as I said, you wanted to divide this array into a part which is at most k and a part which is at most n minus k. How to do that? Well, you can prove, this is an exercise for you, that if there exists a solution, there exists a solution where this number is as big as possible achievable number. So I claim that it's possible to divide into at most k and at most n minus k if and only if it is possible to divide into at most k and at most n minus k, where here you not only chose some subset which is at most k in sum, but the biggest possible sum which is at most k. So let's just try to take the biggest possible sum. How to do it? Let's, in this array, find the kth element. It says whether it's possible to get exactly k. So if it is possible, it is lovely. But what if you cannot get exactly k? Total sum cannot be k. Then let's try k minus 1. Then let's try k minus 2, etc. So let's take the rightmost one in this prefix of the knapsack array. This is your beloved sum. Let's call it S. Then you just want to check whether it's true that S0 plus etc plus S H plus SL minus first minus this S prime is at most n minus k. This is what you need to check. This is how you reduce the problem to one instance of knapsack. Okay, finally problem D. About sliders. Oh my god. So what was about the sliders? So you had some queries. The query says, so there are several, imagine that there is a rectangle 1 by m, and there are several squares. Each is located at some integer subsquare of this rectangle. These rectangles are called sliders, and you have several queries. Move slider I to the position y. So the jth operation is move slider number ijth to the position yjth. Sorry, American quotes like this. Okay. However, when you try to move some slider and it intersects with, overlaps with another slider, then they all become, they continue moving together. For example, if you want this slider to move here, then it will look like this. This slider is now here, but this slider had to move here to the free space, this slider here, and finally this slider here. So they all moved. So you have q such queries. You consider all q factorial orders, and in each of these orders, you look at where the ith slider got. So there are q factorial permutations. Let's take one of them, which is called pi. Then fi of pi is where the ith slider ended up being after the permutation pi of these q queries. And the task was to find the sum over all pi's of fi pi for each I. So this was the problem. Okay, I think my solution worked in square time, maybe. Let me remember. Yeah, probably. My solution works in time something like n squared plus logarithm of prime number. Okay, first of all, how to solve this problem? So I claim that you can find ans I in O of n time plus O of log p precomputation. So this is what I claim. You can find ans I in O of n time. So in total it will be O of n squared. But also before calculating any of ans i's, you need one preprocessing step of log of p operations. Let's find out how to do it. No. Yeah, probably n squared log n. Probably n squared log n. And here we do it in n log n time. Probably like this. Okay, let's look at the ith slider and look at all operations which we do. There are three types of operations: EQ operation, GT operation, GQ operation, and LQ operation. EQ operation simply says make the position of ith slider equal to some number t, some number y. These operations are exactly the operations where ijth is equal to I. So if exactly this slider is moved now, then we exactly know where it will end up being. The second type of operation is make xi maximum of where it was and some number y. What are these operations? These operations are exactly moves of sliders j where j is less than I. Yeah, because if this slider is moved somewhere here, then it did not affect the slider I. However, if you try to move it there, then you also move the slider I. For example, if j equals I minus 1, and you try to say that you move sj to the position 8, this means that you move xi to maximum of xi and 9. Yeah, because if it was exactly at 8 or to the left of 8, then it will no longer be able to do so, because now sj should be at the 8th position. So xi will have to move to the 9th position. And finally, LQ is xi equals min of xi and y. So these three types of operations, we apply all of them in some order. Okay. What to do then? Basically, you need to understand that there are only q plus 1 possible places where the slider can end up being. It can end up at the position AI, where it was initially, or it can be in any of y's. Maybe some of them are impossible, but the only places that are possible are among these y's. Well, actually, these two cases are very different. You can notice that. So if all such y's are equal to ai and all such y's are less than ai and all such y's or equal are greater or equal than ai, then none of the operations can possibly move the element from ai. So the element will definitely end up being on ai, and we multiply it just by q factorial. And this is the answer. However, if at least one of such operations fails these conditions, then the element will definitely move from AI. It might return to AI, but not as AI, but as to one of these y's. So there are two cases. The first case is definitely AI, or second case, definitely one of y's. Yes, it can be that AI is among y's, but you can just ignore this fact. You solve either this subproblem or this subproblem. And to choose which of them to solve, you need to check whether these things called. Okay, the first case is very easy, as I explained, so we now need to explain the second one, when it's one of the yi's. Well, in this case, let's just iterate over all y's. Let's just iterate over all possible y's. And understand in how many ways we end up at this position. Okay, then there is just some case consideration. So let me draw the outline of what will be going on next. So for I from 0 to n minus 1, we choose the slider, which we will be considering. Then we checked these conditions in O of n time. Solved first case or reduced to the second case. Then also if O on n log n time, let's sort EQ, GQ, and LQ. Since the order of them in this list of our operations in the input does not matter, it will matter later, but not the order in which the input is written, but in which we will choose these operations. It matters, but before, after just reading the input, this order does not matter. So we can just sort these things. And then we will iterate over EQ cup, GQ cup, LQ. And we will find number of ways to get X and add number of ways times X to ans I, and then print the answer. So print the answer works in O of n time. So find the number of ways to get X and add number of ways to get answer I. It will work in O of n time, of O of 1 time, with O of P. Let me write O of n plus log P precomputation. O of 1 time plus O of n log p precomputation. If we do that, this is my promise. I will explain it later. If we do it, then while we iterate over all such x's, it will work in O of n time with O of n log p precomputation, n plus log p. And then this whole thing works in O of n squared plus O of n log plus n log p precomputation. And then you can just add precomputation here and get n plus log p plus n squared, which is O of n squared plus log p. Okay, so I only need to explain how do we find the number of ways to get exact sum in O of 1 time. This is done here. So there are 8 types of operations. When we know number x that we are interested in getting, it is called I here. So we know that we want to get exactly number I in the end. So there are several types of operations. EQ operation, make it exactly I. EQ operation, make it some number which is greater than I. And EQ operation, make it smaller than I. Some number to be equal to some number which is smaller than I. Also, there are operations to make it at least j where j is greater than I. So GQ and GQ to get it at least I. And same way there are 2 LQ operations. Also, there are some operations which I did not list. For example, GQ operation which gets the number at least I minus 10. But if it was less than I, it will still be less than I. So in terms of becoming exactly I, it actually does not change much. So we will put them in skip. So skip is GQ with something less than I and LQ with something greater than I. Then there are some formulae which you can check out in the contest period. But basically, to get exactly I, there are 3 ways. Make the last operation I, and maybe insert some skips, because skips never do anything. So these 7 types of operations, A, B, C, D, E, F, G, are called interesting operation. And the rest operations, they are called skipped. Skip operations. They run Q minus K operations. Skip, and all these interesting operation, their total number is called K. Okay, you need to get, if we ignore skips, exactly I at the end. And there are these many ways to do it. It's easy to understand why. How to understand why. Let's just consider all n factorial permutations. Then let's consider the k elements which are interesting operations. Exactly a kth of them end up with this type of operation. The rest of the k minus a over k part of the permutations, they end up with another interesting operation, not a. So you need exactly these many. So the second way and the third way are very similar, so we only consider the second way. In the second way, you need the last operation of type B. The last operation will be A, B, or C. Or there were no operations at all, in which case it is simply AI, and to get the understanding whether the answer is AI, you need to distinguish between Roman number I and Roman number 1 and Roman number 2, which were lower. So you need the operation B, so you need to get the last operation is make the number at least I. In order for this to make the number exactly I, you need this part to make the number at most I. So make the number any number which is at most I, but after that you need to make the last operation which makes it at least I. This means you can prove that if you ignore b's in this list, the last operation except b's should be A or C or E or G, because each of these operations makes the number at most I, but each of the other operations makes the number greater than I, and you cannot use it. So now you need to do the following. You need to consider all operations except b's. Then you need to choose the last operation from the set A, C, E, G, and the rest of the operations can be in any order. Then you need to insert b's in any way, but the last operation should be b. And then you insert skips. You can calculate how many ways are there to do it, and it turns out that there are these many operations with one catch. Actually, if k equals b, then you definitely can make the number at least I, but you have no means to make it at most I. And the only way to make it at most I is if the number AI itself was at most I before the operation started. So if k equals b, then you need to check whether AI was at most I in the beginning, and then you calculate this thing, but instead of a plus c plus e plus g times k minus b minus 1 factorial, you will simply have 1. You have exactly one way to get the number at most I. It is already at most I. However, if k is not equal to b, then you apply this formula. And with last operation of C-type, it is very similar. So that is how you do it. And you need log n precomputation, log p, I mean precomputation plus n, to find all factorials of all numbers, which we will need. It is O of n. Then you will need to take inverse n factorial, which will take log p time. And then again, in linear time, you can find all other inverse factorials by multiplying this inverse factorial consecutively by n, n-1, n-2, etc. So you will have all precomputed factorials, and if you have precomputed factorials, you can also have precomputed just inverse numbers. To get k to the power -1, you can have k minus 1 factorial times k factorial inversed. Okay, that's it. Thank you for watching.